just like this circular. This is the visible edge of a circle. This is a rectangle, so this is the visible edge of a rectangle. Hidden lines basically show what we cannot we cannot show on a particular object as directly. See, this is an object. If I'm drawing its top view, I cannot show this line as well as this line because it is not visible from the top. So the top view will be drawn with this edge is visible, so this is a visible line. This edge is visible, so this is a visible line. Again, this edge is visible, so this edge is visible, so this is a visible line. But this edge is invisible, so I draw it with a hidden lines, that is my dashed lines. Center lines, we use continuous, these lines, thick lines made up of long and short dashes, as we discussed. As you can see, this circle is this is the center line of a circle, and this is another shape that has its symmetry about this particular center line, and this is another center line for the circle because circle is symmetric in all 360 degrees. Dimension lines, these are noted for making the dimensions. These are my rays which extend from both sides and leave the space in between as shown here. Here I write my figure, say 20 mm, 30 mm, 50 mm, whatever it is. Extension lines, these are particularly to show the dimensions. These lines have an endpoint, so this we take it as the endpoint, and we consider these rays end up till here, and we can give the dimension again here. The leader line, this shows wherever we cannot directly write or say the distances between the two endpoints is very small, we use the leader line to show its diameter or to show its measurement or whatever. Fathom lines, as we discussed, the initial position and the final position. The initial position is drawn with a continuous thick line or the visible line, and this is the fathom position which will be drawn by the fathom lines or say the datum lines. The sit-on lines, this is a stitch line. Stitch line is something where, say if this is an object and we have to weld this object, so this particular welding will be contained on this particular line that has been shown. So this is the stitch line that we see. Now the next comes is the break line. The break line, if you have a long line, which shows that this object has been created in between. If we have short lines, it shows a section of the particular object. Cutting lines, it shows that from here there will be an output, and here there will be an output or say input, whatever it is. Cutting planes, now if you want to cut this kind of plane and show the cross section of this particular area, so this is the cross section of that area, and which has been designated by this particular line. Moving on, now we have discussed everything. We have discussed sheet, we have discussed what are the instruments that we are going to use. But for labeling that particular sheet, it is very important that we use this title block in our sheet, which is there on the right hand bottom side of the sheet. Now it contains particularly required information. Apart from this information, the engineer who is interpreting it does not need any other information. So for institutes, this is the particular standard. I'll write the name of my institute. First, this is the title blocks. Now the dimension of the title blocks is 175 mm, that is horizontal line. As well, now this line has 8 parts, 1 2 3 4 5 6 7 8 and 9. 9 is 72, so this is 72 mm long. Okay, the information that I need to put in these particular blocks with particular dimension, name of the college, the place of the college, what actually is my projection. I'm using an orthographic projection or I'm using any other projection. Now this particular, what is this sheet going to be used? It's going to be used for reading, so I'll mention reading. This shows the angle. This is the third angle projection or first angle projection. This diagram will tell me that it is a third angle projection. Then this is my drawing number. If I'm say this is my sheet number 22, or say this is my sheet number 2, so I'll say this is my sheet number 2. On the left hand side, I'll have the date and sign of my teacher. This is my starting date, the date on which I started drawing this particular drawing. So I'll mention the date. At the end of the lecture, I can have a signature from my teacher that I have started this. Then the once I have started drawing, I'll have a rough, sometimes I have a rough structure, so my teacher tells me, or I'll tell my students ki you have to make it fair, so I'll draw it again. So this is the fair date, okay, on which I have drawn the fair thing. I'll have a signature again, and the date of completion is there. Now again, the other important things that we need is we need the name of the students, on which semester it is, the roll number, and the most important of all, I need the scale. I need the scale on which the drawing is done. We'll discuss plane scale later on, so you'll understand what is the particular use of that particular scale. Plane scale. As I said, we are going to discuss scale, so we are using plane scale. Now let us see what a scale is. If say, let us consider, if I need to draw the map, the area, or say the globe, the radius of the earth is 6400 kilometers. How can I depict on a paper? I cannot draw 6400 kilometers on paper, because for that production of that kind of paper I need God to come down. I won't be able to produce that kind of a radius of paper. So what I'll do is, I'll make a scale. I'll say ki 1 mm is equal to 100 kilometers. So I can have the radius of the earth as 64 mm, because 1 mm is equal to 100 kilometers. So 64 mm will be equal to 6400 kilometers. So I can draw the map of earth, or say the globe, on a paper which can accommodate 64 millimeters. So there are two types of scales basically. We have a reduction scale and we have an enlargement scale. For reduction scale, as we discussed an example, that the earth can be summarized in 64 mm, because we have a scale of 1 mm is equal to 6400 kilometers. 1 mm is equal to 100 kilometers. Now secondly, there is an enlargement scale. Enlargement scales are basically for very tiny objects, say electrons. Electrons might have a diameter of say a few nanometers. So for that, to see or draw it on an object, I'll take the scale and enlarge it by say 10 raised to 8 meters, or 10 raised to say whatever scale, but appropriate scale I use. So for that I use an enlargement scale, and for big objects, to make it small, I use a reduction scale, so that I can accommodate this particular thing on my paper. Now this ratio by which we are decreasing or increasing the size of the object is known as the representative factor. Now one thing has to be kept in mind, that if we are using a particular scale, say 1:10, as we saw in the title box, now all the dimensions, all the lines, every object that is there on that particular sheet should be reduced by the same angle. It should not be like I have taken the radius as 1:10 and then I am taking the line as 1:5. No, that is absolutely wrong. The scale that I have mentioned once shall be applicable to all the objects or all the dimension in that particular sheet. What is a representative factor? Now let's take a look at the equation. Dimension, the representative factors can be determined, say represented in various directions. The basic formula that we use is dimension of the drawing by the dimension of the object. Say as we took the example, the dimension of the drawing is 64 mm for earth, and the dimension of the object is 6400 kilometers. So my the representative factor that comes down is 1:100 kilometers. The length of the drawing upon the actual length is again another place by which we can represent the representative factor. The area, in terms of area, if you want to take out the representative factor, it will be square root of area of drawing upon actual area. And again, if you want to take out in terms of volume, it will be the volume of the engineering drawing, or volume as per the drawing that I have made upon the actual drawing, which factor will be then again taken the cube root of. And the length of scale that I need will be equal to RF into the maximum length to be measured, so that I can know that what scale, or say what dimensions can I accommodate on my paper. So the different types of scales: we have plane scales, we have diagonal scales, we have vernier scales, we have comparative scales, scales of chords. Apart from that, we have mechanical scale, architecture scale, we have civil engineer scale. So all these are different types of scales, but we don't need to get into specifics of that. We need to know what is a plane scale. For that, we will discuss an example. Now look at this example and read it very carefully. I'll read it out to you. In a map of 36 kilometer distance is shown by a line of 45 centimeters long. Calculate the RF and construct a plane scale to read kilometers and hectometers for maximum 12 kilometers. Show a distance of 8.3 kilometers on it. So we basically need to accommodate a map which is of 36 kilometers by a line of 45 centimeters long. So for calculation of RF, again I'll say what is my drawing scale. It is 45 centimeters, so I'll divide it by 36 kilometers. So my ratio will be 45 by 36. So now that 36 kilometers have to be converted into centimeters, so I'll multiply. First I convert it into meters, so I'll multiply 36 with 1000, so 36,000 meters. Then again 1 meter is 100 centimeters, so I'll again multiply it by 100, so I'll have a scale of 1 upon 80,000. So this is my RF factor. Now I'll take out the length of the scale. The length of the scale is RF, that is representative factor into maximum distance. So the maximum distance is 12 kilometers, so I'll have my representative factor multiplied by 12, so it comes down to 15 centimeters. So how are we going to draw this particular scale? So let us take look at the figure which is going to appear on the bottom side and know how we are going to draw this particular scale. So first step that we are going to do is the maximum length of the scale is 15 centimeters, so we need to draw a line of 15 centimeters. Okay, now the next thing is we will divide it into 12 parts, 12 equal divisions as shown in the figure. Okay, now we need to label it from 0 to 11. Now before 0 we'll take millimeters, so we will millimeters of the scale and divide it into 10 parts, so 0 to 10 as shown, and this is 5, that is a mid object. Now the next thing that we are going to say is we are going to represent the lines. So this is the scale that we have formed the scale. Now this is the scale is in kilometers, and this particular will be known as hectometers. This is the representative scale, plain scale showing kilometers and hexameters as required in the question. The next thing is I'll take the mark. So the first thing that I need to mark is 8 kilometers. So my first line would be from 0, this is 1, 2, 3, 4, 5, 6, 7, 8 kilometers. So this is 8 kilometers. Again I need 0.3 kilometers, so I'll go back. How much I have divided this into 10 parts, so each part is 0.1. So 0.1, 0.2, 0.3. So this is 0.3 kilometers. So this particular scale will be 8 kilometers and 3 hectometers. So we have this particular scale or the solution for this particular question. Any other interpretation of plane scales can be made in this kind of a manner. So we come to the end of the introduction part of engineering graphics. The brief description of the next part that we are going to discuss is loci of points. This is a very interesting thing. Now we have understood what will be the basics. Now we are actually applying that engineering drawing to a real object. Let us see. First of all, let us know that what is a locus. A locus is a path of the object which follows a certain condition. Now I would like you all to look at me. If I am standing up right now, this is my particular position. Okay, now as I move, just take a look at my hand. This is a particular place, so this punch shows the point. Now as I'm moving from left, 1, 2, 3 steps, so I have moved horizontal 3 steps. Along with that, this point has moved, so the locus of this point would be 3 steps, a straight line of 3 steps. Now again, if I'm going to come forward, so 1, 2, 3. Now I'm coming forward in a vertical direction with this point. So this point again is moving with me. So this vertical line of 3 steps. So I'll trace back the same path, 1, 2, 3. So I've come back to the same position that I was on my first step. Now I'll move 1, 2, 3. So I've come back to my original position, and the point also has come back to its original position. The path that is traced by this particular punch, or say this particular point, is the locus of that particular point. So let's move on. Let's see a more graphic representation. This is a cow which has been tied to a pole in any dairy, or say in any farm. So what will be the particular locus that it can maximum trace? So let us see what all condition we have. A cow is grazing in a field. It moves at a maximum distance of 5 meters from the pole, which will be the length of the string. So what will be the locus of that particular cow? So let's take a look. This is the path that we have to trace. What is the necessary condition? that it should be at 5 meters always from the pole. So this is what my locus will look like. Boop! At the end the cow says, I've finished my circle, so I've finished my locus, so now it's time for me to go. Moving on, another example. If the cow is running on 2 legs, let us imagine a cow running on 2 legs. Now what will happen? This is the cow which is dancing and running on 2 legs. Necessary condition is that it should run in there is a straight level road and it should run in a straight line. So I'll particularly have this condition, the path that I have to trace, and this is the final position of the cow. So this is the particular locus that has been traced by the cow. So another example that we will see to understand what is basically a locus. The two basic locuses that we always encounter is a circle and a straight line. So let us think, a cow is grazing in a field again. It is hungry, so it is grazing in the field again. It is the same question that we took up. The distance of it is 5 meters from the pole, and it is tied, so it cannot go more than 5 meters away. How will the locus of cow look like? It will be, say, but 5 meters. I cannot make a 5 meter scale, so I'll have to take down the scale. Say 1 centimeter is equal to 1 meter, so I can draw the circle of 5 centimeters. So this is how I'll take a center point. I'll take a scale of 5 centimeters. I'll take my compass, measure 5 centimeters on the compass. The next point is, this is my point, this is 5 centimeters. I'll take my pointed part, put it on P as shown by the blue dot, and my circle is ready. So I hope you understand what is the locus. Okay, so this was what all we are going to discuss today. We discussed in brief what is why it is necessary to learn engineering graphics for all the branches of engineering, what all instruments do we use, what all lines are used, what is a locus, and how we can draw a very simple locus. In next session maybe we'll discuss what in the locus and other subjects, other units in detail. So thank you all for being such attentive students, and have a good day.